Welcome everybody to today's webinar of the IEA SHC Solar Academy hosted by ISES. We are very pleased to have all of you here, and we are especially happy to welcome our speakers and you, the audience, to the webinar. We are now good to go. My name is Arabella. I am the Congress's Communications and Outreach Officer here at the ISES HQ in Freiburg, Germany, and I will give you a short introduction into ISES and the work we do, as we have many new participants joining us on the webinar today. So, ISES, who are we? ISES, the International Solar Energy Society, is a non-profit UN-accredited membership NGO, and we were founded in 1954. ISES represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates from countries all around the world. Our vision is 100% renewable energy for all, used efficiently and wisely. And ISES works together with like-minded organizations from countries all around the world, such as the IEA SHC, to advance our renewable energy transformation. Here at ISES, we have a range of key activities to advance our mission. We hold biannual congresses all around the world. One is the Solar World Congress, and one is the conference series called Eurosun, which is now in cooperation with IEA SHC. We have two major publications. One is Solar Energy Journal, which many of you will be familiar with. It's a flagship publication which started in 1957. And then just now in 2021, we were very happy to add to that our Solar Energy Advances Journal, which is our first fully open access journal. Of course, there's much more to it, and we also do webinars such as the one today. We have education initiatives both on-site during our conferences and also online. And we have a set of infographics, and on top of everything, we also have, and we are very proud of that, a solar energy museum in which we trace back the history of solar and the many important developments over the past decades. We are a membership-based organization, and so we invite all of you to join ISES to advance our renewable energy transformation. So for the webinar today, I know we are all excited to get started. Yes, there will be a Q&A session for you, the audience, and we're going to have that at the end after we have heard all presentations. Nevertheless, you can send in your questions all throughout the webinar, and you use the chat box on your GoToWebinar panel for it. If you send in a question, please keep the question short and precise and write who of the presenters your question is for. That's going to make it a lot easier for our moderator to then send the question to the right presenter. And on that topic, I'm very happy to introduce our moderator of today, Bärbel Epp. Bärbel has been with us for many of the IEA SHC webinars, and we are always very happy to have her back. She is the founder and managing director of the German consultancy solrico. She also is responsible for the international newsletter on the portal Solar Thermal World, where she reports exclusively on market and technology trends in the solar heating and cooling sector. And also, for many years, Bärbel now has been the chapter author for the annual Global Status Report published by REN 21. So it's my pleasure to hand over the floor to you. Bärbel, welcome.
Yes, Arabella, thank you very much. Good afternoon also from my side. Yes, I will share with you some slides on what is the IEA Solar Heating and Cooling Program. Will this work? Oh, sorry. Can you share it again? Or was it already shared?
We see your screen. And
oh, you see my screen already?
Presentation is there. You just,
presentation is there.
I think you have to go back.
My presentation is there. Sorry for that.
Yep, there we are.
Okay, sorry for that. Okay. Yes, we have, together with ISES, a very nice and long-going webinar series. It's called Solar Academy IEA SHC. Today we have the interesting topic of solar process heat, and I will give you some insights on the IEA Solar Heating and Cooling Program. It's a research-focused collaboration. 19 member countries and 8 international organizations cover a big range of countries. You see them colored here on the map. You have the red ones, which are direct members, and the orange ones, which are members via sponsors. more than 200 experts from industry and research work together on dedicated solar projects. So we have a lot of topics which are listed here, you know, like water management. We have solar cooling in the Sunbelt region. We have neighborhoods. We have solar hot water for 2023. So we cover a wide range of applications in solar heat. The Solar Academy is the webinars we host with ISES quarterly are one of the activities of the Solar Academy, but there are also others. We have a video channel on YouTube where we have recorded a lot of YouTube's videos with experts on conferences. And what is very important, we offer on-site and online training with solar heating and cooling topics on request of IEA member states. And the last of the such trainings were in the Caribbean, in China, South Africa, and the UK. You want to find more information of our organization, you can go to the website iea-shc.org or follow us on the social media that you find here. Also the YouTube channel I mentioned already. If you want to search for the Secretariat, we give you here the contact information. And then I want to stress your attention to our flagship annual solar heat report, which is published once a year in June. It's the most comprehensive data gathering on solar heating and cooling technology and market trends. And you'll find it also on the website available as a PDF, and you can consult it and also quote it in your own presentations. So this was my little introduction. I'm happy to welcome you today to this Solar Academy webinar on solar process heat. The IEA SHC is organized in tasks. So this is how we call the research programs. Solar process heat has number 64 already. And we have 3 dedicated experts from this task who will present some of their work today for us. This task is a 4 years research program, and they are almost at the end now. They have 1 year to go, so we already see a lot of results coming up. So the first speaker today is Felix Pack. He is researcher at the Institute of Thermal Engineering at the University of Kassel in Germany since 2015, and he became head of this group in 2019. He's currently working on his PhD, looking at a combination of solar collectors with TCP in industrial applications. Within this task 64, he chairs the subgroup on integrated energy systems. And he will present today about the role of SHIP in industrial hybrid energy solutions. So Felix, I'm looking forward to your presentation.
Yeah, thank you very much, Bärbel, for the introduction, and welcome to everybody here in this webinar. I hope you can now see my screen, and as Bärbel already said, I want to talk about the role of solar heat in future industrial hybrid energy systems. Within task 64 subtask A, we focused we focus a lot on industrial heat load profiles, and there we found one thing which is which not that much attention has been paid to so far. So very often, if people think of industrial heat load profiles, they have a constant and flat heat load profile throughout the year in mind. And what we found, based on a broad database analysis, that very often we see also in industrial companies heat load profiles which are very seasonal. So we have a strong dependency of the heat load profiles throughout dependency of the heat load on the ambient temperature. So here's one example from a car manufacturer, and we can see very clearly how the heat demand is increasing with decreasing ambient temperatures, at least on a daily basis. What people have more often in mind is a load profile or a correlation of the heat demand and the ambient temperature, as we see it here on the right side, which is an example from the food and beverage industries. And here we can see the non-dependency of the heat load profile of the ambient temperature. So that is really one thing which is very important to keep in mind. How does the heat load profile looks like, and what is the influence on the overall system design? In subtask A, we yeah, we did some more work on that, and we did a cluster analysis of more than 500 heat load profiles. Unfortunately, these profiles are mainly from Germany. We think that yeah, the basic results can be transferred also to other regions throughout the world, at least in these regions where we also have kind of a yeah, seasonal behavior of the ambient temperature. And here in this diagram, you can now see the results of these cluster analysis. So we have in blue these profiles who are very non-seasonal and flat throughout the year. And for different industries, you can see how the heat demand is really increasing with the ambient temperature. More information on that, and because we think that is very important for the future system design, you can find in this deliverable, which is shown here, the reference applications for renewable heat, which is published on the task website. And there you can also find an Excel tool where you can make your own heat load profiles. So I have already shown in the on the last slide this strong dependency of these heat demand clusters and the ambient temperature. And here in this picture, you can see the combination of the clusters and different sectors, and how the different clusters are distributed within these sectors. So to give an example, again here, the manufacture of beverages. At the bottom here, we have in all our profiles that we had, that all these companies were were collected in this cluster 0. So in these clusters where we don't see any seasonal behavior, and that is very different in some other sectors. For example, in the manufacture of computer, electronic, and optical products, where we see more processes who are related to the ambient temperature, for example. Or basically, this is very often space heating, but also very important are big ventilation units, who are often underestimated in their importance for the industrial heat demand. One other thing that we took a look at in the subtask was the importance or the availability of roof area for solar collectors. Very often in potential studies, we found that the availability of roof areas are a limiting factor, but so far we could not quantify it. Based on the database that we had, we could make an analysis with GIS data from OpenStreetMap and analyze how often the roof area is really a limiting factor, and what is the influence on this potential solar fraction that we could reach with these solar collectors. And the results you can see here in this diagram. So on the y-axis, you can see the required collector area based on the summer heat demand. So the solar system design is always made in a way to really meet the summer heat demand and not to produce too much excess heat in summer. And on the x-axis, you can see the flat roof area that we find based on the GIS data. And always, if you see now, so one dot is always representing one of the companies in our database. And in all cases where the company specific dot here is below these lines, then you know that the roof area is big enough to install that much solar collector area to really meet the summer heat demand. And the good news is that only 40% of the companies that we had in our database had a too small roof area to install enough solar collectors. So basically, this is a quite good result, as 60% had enough roof area. Nonetheless, it also underlines the importance of having already during the installation of new industrial areas, also having already there in mind that you need to have enough perhaps additional areas to install solar collectors. So what is now the influence on the solar fraction? Both of the roof area and the load profile. Sorry, and here you can see yeah, again, a combination of these both analyses. On the x-axis, you can see now here the relation of the collector area that we calculated based on the load profile, which is possible, divided by the available roof area. And on the y-axis, you can see the solar fraction. In this case here, again, every dot is representing one company. And here the roof area is not yet seen as a limiting factor. So this is really just what is possible based on the roof area. And we can see here, blue are these load profiles with which are quite flat. So we can see a high summer heat demand where we can, and based on this, we can really reach a high solar fraction in the range of 30 to 40%. But the more seasonal the heat load profile is, the smaller is the solar fraction if we design the solar collector field according to the summer heat demand. If we now also take into account the available roof area, then the picture looks already a little bit different. Then we see always if the roof area is a limiting factor, the solar collector area has to be decreased based on the available roof area, and then also the solar fraction is partly massively decreased. And this is especially the case in these companies where we have a high summer heat demand, so especially all these blue dots here. And based on the median, you can already see the decrease of the potential solar fraction that we can reach. So what is now the yeah, what's now about the combination of solar with other technologies, which is what really one basic part of the work that we do in subtask A. Based on the analysis of the load profiles and the available roof areas, I think it's quite clear that there are a lot of applications where we have to combine solar with other technologies, and we put an effort on the combination of solar and heat pumps in subtask A. And we were quite surprised in the beginning of the subtask work that everybody is talking about the combination of solar and heat pumps, but if we talk about details and really how to design the systems, everybody has its own strategy, which is based on its own experience, but there's not yet a really established common system design methodology. So what we did is to analyze a lot of parameters with a simplified calculation model, really to find out what are the most sensitive parameters. So as you can see on the right side, one basic idea was to have a look at different system designs. On the one hand, having solar collector field and heat pump completely in parallel, and then also two system designs where the solar collector field does a preheating and the heat pump ensures the set temperature, and vice versa, that the heat pump is doing the preheating and the solar collector field is designed to really reach the set temperature. And we wanted to find out which are really the basic parameters that are influencing our system design or our economics. And I cannot go into all details, but I want to show you one slide which is kind of summarizing what we did and which is going to be published soon, hopefully in a solar energy and advances paper. That here you can see in all these diagrams the levelized cost over 20 years for the different system combination of solar and heat pumps, and some parameters that are less important here at the top. So the location, the hydraulic concept, and also the annual load profile type are not that important for the economics of the system. Of course, you have different system designs and different solar fractions that you can reach, or renewable fractions, but for the overall economics, it really does not make too much of a difference. But here are three other parameters that are really making an impact and having an impact on the levelized costs. And on the one hand, this is a daily load profile. So is the heat demand throughout the year more or less constant, or do we see a peak during noon, or at least during the day? So that's really because that has an impact on the system design of the heat pump, and that you can see also here, shown by the heat pump capacity ratio, which is defined as the heat pump capacity divided by the maximum heat load, which we can see throughout the year. And here we could see that a strong under-dimensioning of the heat pump has really a system on the levelized cost, but the lower the heat pump is designed, the lower is also the amount of heat that can be delivered by the heat pump. So that is kind of a trade-off that you have to do. But going into the direction of 100% renewable systems, our proposal is going to the direction of a 0.5, 0.6 heat pump capacity ratio system design. And also quite clear, the source temperature for the heat pump has a relevant impact on the efficiency, and so also on the levelized cost of heat of the overall system. Again, if you're interested in more results on that, I invite you very much to have a look at this paper if it gets published soon. So to summarize, heat load profiles in industry cannot be assumed to be constant, as this is done very much. It really depends on the location that you look at, and on the sector of the industry where you want to integrate solar collectors. But the good message is almost all companies have a relevant summer heat demand. So there's always a role, at least in minimum, to cover the summer heat demand. Another conclusion, the roof area is a limiting factor for solar system design, but the majority of the companies really has enough roof area, and that is always the easiest option, not always the cheapest option, depending on the availability of other areas. But nonetheless, it's quite important to see that roof area is not a limiting factor for all companies. And one really important result based on our subtask A result is that we need new design strategies for solar heating plants, especially in combinations with other technology, especially in combination with heat pumps, but also having in mind that the heat load profiles are very often not that constant. And so if we have the heat demand in winter or the transition times, but the solar yield in summer, we still have to see how to really better combine that to reach higher solar fractions or renewable fractions. That's what I wanted to present. I thank you very much for the attention, and I'm looking forward to your questions in the Q&A session afterwards. Thanks.
Yes, Felix, thank you very much. Very interesting. I think especially this hybrid combination, because we need to go to higher shares. So there will be always this offering of hybrid solutions in the future towards industry. Very interesting. So we will have all questions, as Felix said, at the end. And I want to stress as well the fact, if you take part in the webinar on Thursday morning and you're listening to the recording, we also encourage you to type in your questions, because we can read them out at the end of the recording, and we will answer them also in the following Q&A session. So both ways are possible. So then we have our next speaker. I want to welcome Dr. Alan Pino. He is researcher at the Energy Engineering Department of the University of Sevilla in Spain, where he obtained his PhD about solar integration in microbreweries. He's particularly knowledgeable in the field of solar resource assessment and integration of solar energy in industries. And Alan is originally from Chile, where he worked at the local Fraunhofer Institute in Santiago before. So today he will share with us insights about evaluating the uncertainty derived from ship plant simulations. A challenging topic. I'm looking forward to your presentation, Alan.
Yes, hello to everyone. Thank you very much, Bärbel, for the introduction, and ISES and HAC for the invitation to this webinar. So as Bärbel said, I will speak about the evaluation of the uncertainty related to the simulation of chip plants. These activities are part of subtask C of task 64, and the leader of the subtask is José Miguel Cardemil. And all the other authors that we have listed here, we have self-defined as a core team because we have not done all the work that I would present, but we were organizing and exchanging information with all the other participants of the subtask. So first, to start with the objectives of the subtask, it is to develop, well, collect in the first place and develop new information about simulations and monitoring tools for assessing the energy yield, especially for chip plants. And the most remarkable item here is that we want to address the known uncertainties that affect or impact the simulation results. And for this, as I said, we first collected information because we're not starting from scratch. Task 49 was done several years ago, so we identify and evaluated the available simulation tools that we started from there, and all the new tools that have been developed in these years. That was, well, the first part of the task. So this is a 4-year task. The 2 years, well, almost 3 years are already completed, and these 2 main objectives we have achieved, and the next one for the next year would be the 3rd one. So the second objective, so this is the one that require more effort and more activities, is to assess the uncertainty that we can have in modeling simulation, modeling chip plants in different simulation tools, especially those that are developed for solar process heat systems. I will speak mostly on this. And then the last part of the task, which we are launching in the next days, it's to do the yield assessment for the monitoring stage during the operation of the plants. So this way it would be easier for the client and also the supplier of heat to have clear measurements or some guides in order to understand and to improve the contract, because it's very customized right now. This subtask is also related with the other subtasks, like the one Felix just presented and the next one that Wolfgang will. What are not objectives of this task is to make a ranking of the best tools for simulations. That is not possible because it depends a lot of the user, and also, well, it won't be fair to many tools, and also we are not wanting to create a tool that is the reference or the standard to simulate chip plants in this case. So just wanted to clarify that. How we did this work, so the methodology, well, I will briefly explain it. We started with case studies. So these were actual plants that are in operation, and we needed to have some certain relationship with the owners or the operators in order to get important information about the design. So we defined some plant parameters that were or usually are requested at the simulation tools in order to build the model and simulate it. And then we did the simulation in different software. By we, I don't say this core team that I mentioned, but all the many participants that they have licenses of commercial software or even in-house software developed. So they said, okay, I want to simulate in my software and give me the plant parameters. They did that, and then they submitted to us all the results. We made a comparison of all the results, and on that point, we could identify some sources of difference. This was mainly collecting information, all these stages. We also did a lot of bilateral meetings with the analysts, so we could directly ask, why do you think we have this difference here? Is because you did an assumption, or is because a limitation of the software? So we collect a lot of qualitative information about the sources of difference for the energy yield within the different softwares. Then with all that information, we define some assumption scenarios. That being, we created in one tool a very detailed model, including everything that could be possible, and then we started relaxing some of the constraints. For example, trying to emulate what happened when you cannot model something because of software limitation. We did that for all the case studies that I will present next, in order to understand how the technology impacts on it, how the load and the integration scheme also affect it. And from that results, we obtain the overall results. So it's a guideline that I will also show you. So for the comparative study, we had 4 case studies. The first one is a flat plate collector plant, fixed, and it supplies heat to a copper mine in Chile. This is the picture. The second case, it's a flat plate collector, also solar field, but it has one axis tracking system to supply heat to a paper mill in France. And this already was, even it's a simple technology, it was not easy to model in all the available software because it's not common to have a non-concentrating solar thermal system with tracking system. So it was also interesting to do this. This is a Fresnel collector to supply direct steam to a process also. And again, a different technology with different temperatures, and also storing steam is a challenge by too many softwares. And the last one, it's a parabolic trough that supplies heat to a dairy factory located in Switzerland. So the table here shows the software or tools that we analyzed for each of the cases. Of course, the most more tools are better, but it was not always possible, mainly because of limitation of some of them. In addition, we had, for example, for transies, which is a very you can make a very customized model. We had different results from depending on different analysts. So we also can kind of assess the impact of the human, and we wanted to avoid that in the later stage. So recently, the guideline, this is one of the tangible deliverables of the subtask. It's out, it's ready. So we have the draft version. In the next days should be the final one. It presents the methodology that we applied, the detail of the case studies, like all the parameters that I mentioned, and also the integration scheme, which is also interesting, and it's important to know the different on the technologies that are applied. We did the first assessment of the deviations that I just mentioned, and then we related them and tried to list the most common assumption and how they impact in the energy yield. We also present for all the case studies the different scenarios of this induced error assessment. I will show an example just after this slide, just to understand. And finally, some recommendations. These are just recommendations because it's not possible. So chip plants are very customized to the client, so it's not possible to have just very strict kind of articles. It's better to have just some recommendations, and there's no standard nowadays. So for the scenarios, we, for example, consider some parameters. We identify these from the exchange with the other analysts, and some of them are listed here, like time shifting, and this is very easy. For example, when the software is reading the meteorological file with a different time or a delay, a gap that can show some problems, and well, thermal capacitance, the pipes insulation if there is a test node, and the load. Also, that's important when you have ramps or if it's a flat load. We have just seen that the effect, for example, in the presentation of Felix. So we just consider some of these parameters, and we then perform the comparison using some statistic metrics, and we separated them between according to the time scale. So, for example, we use solar fraction for total of annual and monthly values, and also the energy delivered on daily scale. But we know that totalizing the energy also hide a lot of variation, so we consider also an hourly scale. And we employ dynamic time warping and residual values to analyze this. Of course, it's a lot of information to introduce it, but we could understand and identify some sources of uncertainty with the hourly values. The comparison methodology that we developed it for case study A, and it was a lot of effort to trying to understand and to decide which are the best statistic metrics to show this information. We obtained we wrote a paper that has open access. At the end is the link. And we also coded everything in Python to perform automatically all the comparison of the different results that the different analysts were sending to us. This is the example, for example, for case study A. It's a table. All the columns show the different parameters that for this case study we consider. So scenario 0 would be the reference. So these are the values considered, and the other scenarios are varying one parameter. For example, time shifting, these are the variation of this value, thermal capacitance, and so on. So these different scenarios show different results regarding the energy to load and the difference comparing with the reference. And for example, here these scenarios consider the thermal capacitance at the solar field. So there's the reference value, and then you can have like no thermal capacitance or having 150% more or even 300% more. And we can see in the overall results on annual values that the difference that you can have is about less than or about 3%. That in simulation is not that important for the overall results, of course, depending how detailed you want it, but it's not a huge mistake considering that you are having an error of 300% on thermal capacitance. But for example, if we consider the number of nodes of the thermal storage tank, if you have a stratified tank and you cannot consider all the number of nodes that you want, this could lead to a quite important error, for example, and that is just because it's a limitation of the software, or maybe because you could consider that it's not that important, but here the results show that it could be you should put more effort in that part. So this would create a guideline in what to put more effort and focus when you have, of course, limited time and limited software, or there are limitations of the software. And also they are separated by technologies on the four that we have studies in this case. Just to show you the hourly data, so we created some residual values plot, and here we can show, for example, these are the number of nodes of the thermal storage, and even for 10 nodes, you could see that the overall annual value is not that much, but you have underestimation and overestimation along the day. So the total value, of course, is not that much, but on hourly basis, it could be important. And if you have in a process where you are supplying this heat, that could also be a problem. So this analysis was also done for all the parameters that we observed, and it is also reported to understand or try to put more effort in those that you can see that impact the most. For example, here also the effectiveness of the heat exchanger. It could depend on the parameters and also the technology. An additional outcome of the work that we have done is to update a table. So this was one of the outcomes of task 49. We took this. It's a list of available software to simulate thermal systems, solar thermal systems. We updated it. Of course, the software have improved in these years, and also they have more capabilities, so we can see, for example, some of the features of the software. They are sorted, and as I said, they are not ranked, which is the best one, but you could see more or less if it could be feasible to model your system in some of this software. It has three. Well, this is a complete table. Of course, if you have any input, we are very open to get it, some feedback, and to add more software. If you have one software, also to include it in this list. Just the final remarks. So I just want to invite you to participate in the second stage of the task. So it's the next year. We will be working on monitoring the solar thermal system during the operation stage. Most of the work done was during the design stage. And for that, our next subtask meeting is this Friday, 2 p.m. Central European time. If you're interested to participate, we just discuss. It's very, very friendly environment. Just send us an email and you can. We will include you in the meeting. All the information that we have shown, the outcomes are available or will be available at the Task 64 website. Here is the link of the open access paper that I just mentioned, which has all the methodology, and it's very academic, so that's why it's not. I don't have time to show it, but here's the link if you're interested. And we also have performed some presentations at the ISES conferences, Sarajevo Congress, Eurosam, and also at the CS conference. I'm very open also to question, and I hope it has been interesting for you, and we have an interesting Q&A session. So thank you.
Yes, Alan, thank you very much. This was great, great insight into, the very difficult topic of simulating complex ship systems. I think important work that a task can do in a very good way, because you have this over institute network, so a lot can contribute. Hopefully somebody is very spontaneous and can take even part in your meeting on Friday. So we come to our third speaker for the day. He is Wolfgang Gruber-Kratzel, and he's research assistant and project manager at the Austrian Institute, INTEC, since 2013. His focus is on industrial systems, including energy and resource efficiency, and innovative process and supply systems. He is also supervising projects focusing on industrial and municipal wastewater treatment plants. He is one of the initiators and long-term administrators of the ship-plant.info database, which is an online database which includes a large number of ship plants worldwide. And I think his topic of today will base on looking into this rich database. Here, the title of his presentation is Ship Successful Plants Worldwide. Wolfgang, the floor is yours.
All right.
Yeah, perfect.
I hope you see my correct version of the screen.
Yes.
Perfect. All right. Then welcome to my presentation on ship successful plants worldwide as part of this academy. I'm glad I can also join my excellent speakers. It was very interesting also to listen again to Alan and Felix. I want to go not so much on the detail of single simulation or concept designs, but rather what has been successful so far. Starting at this graphic, the potential is huge for thermal demand in industries. I think many have seen this chart before. It's an excellent chart showing just how much potential is actually for solar heat in industrial processes. 1/3 of the total final energy consumption is for industry, and again 3/4 is for thermal, so for heat delivery. And then again, looking at the temperatures, again a high share is for temperature levels that are suitable in principle for solar heat. So I know some people that are joining know a bit more about solar thermal. Some maybe don't know that much, but yeah, of course we can think of a lot of barriers, a lot of problems, or a lot of challenges. But we wanted to focus also in this task on the success factors for SHIP. So I want to present today some of these success factors on existing SHIP plants, what we have learned from our SHIP database, as Bärbel has mentioned. And this is why I want to show you some data from these existing plants, some examples, and see what kind of success factors we can derive from them. So this is the link to our existing database. It's this the URL ship-plants.info. You can see a screenshot of the map worldwide. More than 400 plants have been documented so far. You can filter for countries, from operation time, industrial sector, unit operation. With this we mean different processes that are targeted. You can filter by collector area, by collector type. Also point of solar heat integration, which was an important work of the previous task on SHIP on task 49. You can see here an example of the different integration schemes on supply level or on process level. And last but not least, you can also filter by solar thermal engineering companies. So those companies that actually implement the successful implementations. This data from the SHIP database goes directly also in a publication that Bärbel has already mentioned at the very beginning. It's the Solar Heat Worldwide report, which is published also from our institute. Werner Weiss is the main author here, and I'm also contributing in terms of the SHIP data. So in March 2022, this was the last cutoff date, we have documented 394 plants worldwide. In the meantime, a lot have fortunately we could add to the database in the meantime. So we are already looking towards the next publication in 2023. So more than 1 million square meters of cross area have been documented there. Looking at this chart with different size categories, we see that only 3 plants are in this largest category with larger than 30,000 square meter of gross area. And many know maybe that the reason is that it's related to one plant that has 59% of installed power of all SHIP plants. This is the Glass Point system in Oman, which is very huge in comparison to everything else. So all the statistics are somehow a bit difficult to show, because like one plant of this 394 has 59% of installed power. On the one hand, it dwarfs what is happening at the other plants. It also shows the huge potential it can have if the right potential is if the right system is applied. But I also want to highlight that all the other plants, they are success stories, of course. And there's, as Felix has shown, I think that there are many plants with a lot of roof area available for solar thermal. But well, one success factor here, of course, was the turnkey solution. ClassPoint is delivering steam and not collectors, so it has not sold the collectors to the client, but rather it has sold the steam. Another, so this is like I want to highlight as one success factor, this turnkey solution, selling heat, not collectors. We are doing a lot of work with industries, also not only about solar processes, but also of heat recovery and these hybrid systems with heat pump solutions. And of course, for industries, long-term energy security has gotten increasingly important. So having a stable energy price is really a selling point, an increasingly important selling point for industrial clients. They are looking for safe energy supply. Another example is the Molterie in Issoudun in France, which has been implemented in 2021 by the collector manufacturer Savo Solar and the ESCO New Heat. They are selling, New Heat is selling the heat to Beaumont, which is the Molterie here. I'm very happy that this plant is realized. I was at this plant 4 years ago doing a feasibility study, and now it has been implemented. So it's also, I think, a great success that this is was possible. Yeah, also one of the largest collector fields in Europe and worldwide for SHIP. So looking again at the perspective of the end users, they want to know if SHIP is a reliable solution, if it's a simple solution, and if they are the first one to implement, or if it has been done before. So all, we are R&D and suppliers in this research task, and we can say yes, SHIP is reliable. It's also simple, one can argue, but still it's a simple technology that can be implemented, and there are experts that know how to do it. And no, it's not the first time it is implemented, but it has been done before. Then the end user is looking at the financing. It's looking at the CAPEX and the OPEX costs. You can see that, SHIP is rather cost intensive upfront, so very high CAPEX cost, but low OPEX cost. So we try to avoid looking at payback time, but rather look at levelized cost of heat, because this shows more the true cost of solar heat in industrial process, especially if you can provide turnkey solution. Of course, especially for Europe, but also other regions, this has also changed dramatically, while gas price has, from looking at 2015 compared to now, 2022, the gas price has increased significantly, while SHIP has more or less stayed on a same level. So this is, I think, and we think, important selling point. On the one hand, secure energy supply, increasingly higher renewable shares, which is very important, and lower prices. What else can we derive from the SHIP database and the data from there? Again, a chart from the Solar Heat Worldwide from 2022, which bases on our SHIP database. We can see a high number of flat plate collectors. 174 have been implemented as flat plate collector, 59 as Bollock trough collector. I think this is also interesting, but also evacuated tube collectors and other collectors have been implemented through all collector types, in fact. What we have seen in this last year is more implementations on systems with higher temperature on collector temperatures. So Fresnel collectors, parabolic draft collectors, but also this example, vacuum flat plate collectors that can provide up to 180 degrees. We have seen multiple implementations there. There, the integration is simply easier. You can integrate on the supply line on the utility side of the industrial plant. You're talking with the facility managers and not so much with the production managers that are dealing with the product processes, really doing the product. So it's much easier to actually integrate a larger share of the heat. and cover a larger share of the heat demand, which also is also reflected in the economy of scale. So you can install large systems. Well, and future innovations, of course, is the hybridization with heat pumps and also seasonal storage with excess heat combinations. So excess heat, of course, is also a very important aspect. A lot of it is at low temperatures from cooling systems. So integrating this together with heat pumps and solar thermal can result in very high renewable shares. So this is then really the possibility of providing high renewable shares with cost-effective solutions that would be really interesting for the end users. Next, shipper sector, we can see that we have a high share in the food sector, 130 plants, and also the square meters is quite high. Again, mining is the most important one, because again, there is this one large plant included, and also the second largest plant, which Alan has also shown as a case study. This is the Chile copper mine, is the second largest plant with more than 30,000 square meters. So this is very dominant. But besides this, we can see that the food sector is also a very interesting industrial sector for solar heat and industrial processes. And we can see that some companies have really achieved a high number of implemented systems. So they have multiplied what they have done before. They have a high standardization in their workflow. And here I want to highlight the success story in Mexico with two, but also some more companies, but basically two companies that are having the highest market shares there, and they are in competition. They have reduced planning costs because of doing similar integration schemes. Again, when we look at the integration concepts, a lot of integration on supply level at low temperatures was possible, with lower solar shares, but still, and this is why also smaller systems, but still are high standardization, high multiplication. They have been in contact with a lot of industries, so they know how to promote the systems and how to play the selling points. So there's a high replicability in industries. So I think this is also important, that if we reach a tipping point for solar companies, that really accelerates their business model. If they can have increasing numbers of systems implemented, then it increases the chance of snowballing for larger market shares. I wanted to start with all these three success stories, just a few examples to highlight this. And now going to what we are doing in the task 64. We have seen subtask A with Felix and subtask C with Alan. We from AEE together with Fraunhofer ISE are leading the guideline to market. So we really want to make sure to promote SHIP also the right way, to promote it as a solution for the industry. This is the goal we have here. So the big picture is addressing the relevant aspects and barriers, and place SHIP as a core part of this hybrid industrial energy systems that has been presented before, being a platform for researchers, technology suppliers, project developers, and end users. So also today is a good chance to promote this again in the final year of the task. If you're interested in our activities, please also contact us, and we can collaborate here, which would be also very interesting for us in the final delivery, which we are doing, which is a position paper on SHIP. And I think the more voices we can include there, the better it is to speak for everybody. These three aspects I want to highlight: innovation, competitiveness, and financing options. this is also reflected by these 3 success factors I've mentioned. So innovation is still necessary. SHIP is a technology that can be implemented as is shown in the SHIP database. It is competitiveness is important. Yeah, and increasingly looking at financing options. So those were just a few examples. There are many more examples on our SHIP plants.info site, which is done by us. It's a plant-by-plant documentation, but I also want to highlight that there's also solar payback, which is done by Bärbel Epp by Solrico. There's also she's doing a yearly solar supplier survey. So there the suppliers are saying how many plants they have submitted. Also, some of those plants come with fact sheets and pictures. And we collaborate also between these 2 data sets on data acquisition and also cross-referencing. So for example, if you go to the solar payback side, if you look at the suppliers, you can select some of the solar suppliers. And for example, you can select a company. And if you click here on the link for references, it refers to our SHIP database, where we have then a plant-by-plant documentation of this solar supplier. So kind of cross-referencing of this information. Actually, we can cover currently 82% of the collector area that is mentioned by the solar suppliers. So there's a gap, but also we have rather larger systems here documented. And of course, yeah, some will always be missing. We rely here also on all of you in the audience. So if you know of any plants, then please contact me. This would be very helpful. We try to build up collaborations throughout the whole industry to make sure we can get all the data that is needed to for that purpose. Also, you can profit from this information. You can get to Solar Payback for pictures and fact sheets. So for basic information on suppliers, and you can also go to the SHIP database, where you can get a bit more detailed information on the actual location, also some pictures included, more information on the size of the systems, the storage system, the process integration type, lessons learned, and other information on the plants. A small teaser also from our side, we want to relaunch our SHIP database. Will be the same name, but we have implemented it many years ago. Now it has become the time to relaunch it a bit. It will have more features on filtering, a new map layout with plants location, automatic charts and data exports for other researchers to use this data for their market research or analysis. And like it is now, you can add and edit new plants. We are always looking at any addition, so and will then publish it, so to make sure that there are only plausible data published. And well, we will release this in 2023. It's currently in development. So with this, I want to end my presentation. If you are interested in any information on the SHIP database, I highly welcome you to contact me if you want to know more about it. And well, thank you for your attention, and looking forward to your questions.
Good morning, everybody. I welcome you to this Q&A session of our second webinar, which concerns our solar process heating task. I hope you enjoyed the recording. We are here together with the 3 speakers. They are now live on stage. You can join me, and we will have all your questions being answered. And thank you for typing in more questions. You join me as well, the others, and yeah, I think we have already some interesting questions. So We will start with the first speaker. I would say that Felix, somebody wants to know, what do you mean by cluster in your bar diagrams?
Yeah, we, as I presented, or as you have seen in the recording, we analyzed the correlation of the heat demand with the ambient temperature, and we tried to find a way to generalize our results, and that's why we defined these kind of so-called clusters, which are the results of the cluster analysis. And so we did not want to work with the different industry sectors, because there we found that there's a certain certain variability within every sector. So, and these clusters are a method to put all companies with the same ambient temperature dependency of the heat demand into one group. So that's more or less what the clusters are.
Okay. You also talked about roof availability. So we have a participant, he wants to know, is it the weight of the solar collectors that limits the companies to use their roofs, or what do you study in this point?
Yeah, so in our study, we really just analyze the general availability of roof areas. And we worked with GIS data from OpenStreetMap, so it was not possible to estimate the stability of the roofs. But yeah, you're right. Very often that is kind of a problem to find out, or to really analyze if the statics are sufficient to really take the solar collectors. But there are also some. So very often it's not really the static load of the collectors which is a problem, but the dynamic load due to wind loads. And here we see some new developments, especially for vacuum tubes, which can be put very with a very low slope onto the roof, so there are nearly no wind loads. And then very often this should not be that much of a problem, because the static load is typically not the problem. But that is a point that we could not consider in our studies. We really just analyzed the ratio of areas of solar collector area and the available roof area.
Okay, all right. I think this topic of combining solar with heat pumps is of high interest. And we have a question here. Your chart showed that LCOH was lowest when the heat pump capacity factor was 0. So does this mean it is better to have not just just solar and no heat pump?
Yeah, so in general, this that was one outcome of our of this analysis. But here I have to here's one strong point. All the economic analysis always depend very strongly on the energy prices that you use for your calculations. And we used some fixed prices before all the energy price crisis. And it is not really easy to estimate what will be the energy price ratio of gas and electricity within the next year. So we were more interested about the sensitivity of the parameters than in the absolute value. So we could show that by decreasing the heat pump size, we could decrease the levelized cost of heat. So that is generally possible, because then the heat pump has more operating hours. But on the other end, we also have to see that the renewable fraction is also decreasing then significantly, and that is something what we think is not the way that we have to go into in the future. So there's always some kind of a trade-off. But the more interesting result was really that if we go into the range of the heat pump capacity factor of 0.5, that looks like a very good first estimation for the heat pump sizing, because going or increasing the size did not deliver a higher renewable fraction, or at least not a significantly higher solar fraction. And yeah, and there's also not an decrease or increase in cost. So that is, it seems to be some kind of a first guess optimum.
Okay, thank you. So we go over to Alan. I think you have some challenging questions with your simulation. There's a participant saying, in your experience, which of the softwares analyzed in your research paper provides the best compromise, between flexibility and accuracy in the analysis of solar thermal systems?
Okay, so yeah, it's a challenging question, and I think I'm not able to answer it completely. So I just want to clarify that it would be unfair to name one software because we didn't analyze all of them, and we didn't use the most experienced analyst on each of them. So it's kind of tricky, but of course there are some software that have more flexibility. I could say, for instance, Transys is one very flexible, but it also depends on the experience of the user. But anyway, within our software or the software that we analyzed, it could depend on the technology because there were many of them that could model with more detail or less detail for a pre-feasibility analysis, for example, some technologies. And also there's a problem when you are looking into, let's say, when you're looking into the proper, let me think about it, how to say it. So when you have the different software, you get the results, or what we did in the research paper. We compared them, and then we try to analyze on which software, where are the limitations for different technologies. So of course you could have more flexibility, but that could incur in more differences because you need to make more assumptions, or you could have a more broad or more coarse result with a prefixed result. And also regarding the technology, what I said, you could also try to model something in a software that is designed for another purpose, and that won't be a better result in terms of the specific technology. So I think it's quite difficult to understand or to just answer the question with one. Yep.
Okay, thank you. Wolfgang, there's a question. In which industrial processes focus was the study you did for developing your ship plant database? What was the focus when you started developing the database?
Well, which industry sector, you mean?
Yeah, was there a special focus when you started putting up the database?
When we put up the database, this was in the previous task for SHIP, which was task 49. So yeah, many years ago, actually, we didn't have any particular industrial sector in mind, but rather tried to make it as open to all industries as possible. Of course, due to the actual existing number of plants, the food industry was a strong focus, but also others. So there's no particular scheme for this. What we don't include, if that's maybe not clear for everybody, what we don't include is something solar heat for hotels or hospitals, and yes, that's a limitation. We do include agriculture purposes for drying goods. This is sometimes a discussion if it should be included or not, but we do include it. And for the statistics purposes, we only, like for the solar thermal world report, we only include plants larger than 50 square meters. But we do collect information also from smaller plants. Just for the statistics later on, we exclude them again. This is in the community defined because SHIP has a nature of being rather larger plants, so we wanted to stress this.
Yeah, this makes sense. Yeah.
Yeah, broad answer. I hope this helps.
No, that's fine. Yeah. How about the use of unglazed collectors in series with flat plate collectors? Might the low cost of unglazed collectors be a cost competitive preheating solution?
Yeah.
Have you studied that?
I have seen, I know of plants where not particular unglazed, but the combination of cheaper single glazed collectors with more expensive double glazed or yeah, simply more expensive flat plate or other collectors in series. So really using the okay efficiency at lower temperatures and the better efficiency at higher temperatures. I don't know of a combination with unglazed collectors. I think for industrial purposes, this temperature range can in many times be covered also by waste heat from cooling, for example. So most of the time you will find, many times you may find, yeah, heat recovery possibilities from excess heat in this area. So
Okay.
this might be a reason why this is also not implemented. But
Okay.
there might be cases where this is suitable, and I don't want to dismiss it
But
right
you
away.
don't have it yet in your database.
Yeah.
Alan, there is a question. What do you think it is possible to just use a freeware for all the different steps of the project if you develop a ship project?
No, I don't think so. Not for example, for the detail engineering or the last stage of the project. I think it's not possible. But well, maybe not a freeware, but you could, or maybe you could use a base software and you can adapt and develop your own libraries to better model the components that you have. For example, it also depends a lot on the technology, and I want to stress this because many software have been developed at the beginning just to model one type of collectors or system, like the overall system, boilers and everything like pump and the control system. And then they have expanded to other technologies. So some freewares are just focusing in one type of technology, like concentrator collectors. And then you could take this as like the simulation engine and take this and develop yourself, develop models. So I think it could be possible, but then it would be the problem of the validation of this result. So the model could be validated, but you know, if in simulation, if your inputs or the model is not well defined, the output could be anything. So I think at the beginning, at the pre-feasibility stage or feasibility stage, when you're doing parametric analysis to understand the sensibility of the different values or parameters you're using, it is completely possible, and it could depend on the software that you have chosen.
Okay, thank you. Yeah, I think there's a last question. Felix, it might be for you, but challenging as well. Do you foresee that relative humidity or other environmental variables would impact deployment of ship systems in the tropics, for example, in Colombia? Our ambient temperature variation is small.
So regarding the heat load profile, it depends on the processes. So if you, I don't know, for example, if you have a drying process at low temperatures, then perhaps the humidity of the ambient air might be or might have an influence on the heat load of your process itself. But I wouldn't expect that the influence is that large. And yeah, our analysis was really based on heat load profiles where we saw a seasonal behavior of the ambient conditions. So it's not easy to really simply transfer to the tropic climate. Regarding the operation of the solar collectors itself, I would also say that I only see a minor or even negligible effect on the efficiency itself. So yeah, I hope that answers the question.
Okay, perfect. Yeah, I think we have answered all the questions from our audience. Thank you very much for participating. Thanks for the speakers for the engaged Q&A. And I hand over for Arabella for the last indications. Thank you very much and have a great day.
Thank you very much, Bärbel, and thank you very much to the speakers and you, the audience, for the questions. Before we close, one last announcement. We will have a webinar recording ready for you, and we will also have the presentations given by the speakers which you saw on the broadcast, and they will all be uploaded to both the ISES and the IEA SHC Solar Academy homepage. This will take a few days, and then they will be there ready for you to rewatch. If we are joined by any ISES members on the call today, please remember you already have unlimited access to all past webinars via your ISES members area. And then for my final announcement for this morning or for today, we also want to invite you to our next and final upcoming webinar for 2022. And that is going to be on also an IEA task, but that's IEA PVPS task 16. And they're going to have a webinar on all sky imagers benchmarking. And we're going to have that on 15th of December. Registration is open. You can see the link down below. It's on the ISES homepage. And we welcome all of you to join. And this one will also be recorded, so in case you need to catch it afterwards. And with that, I'm happy to close. Thank you very much for joining us today. Stay in touch. You can always write to us at public.relations@ises.org if you want to share any feedback. There's also a small feedback survey coming your way just after the end of the webinar. And of course, we are online. We are on all the social medias, so always a good idea to follow us there. And with that, thank you very much to the speakers, the audience, and enjoy the rest of your day. Goodbye.
Okay, bye-bye. See you.